All right, hello. My name is Cameron Castillo. I'm an electrical engineering student at Oregon Institute of Technology, and I'm going to be talking to you today about modeling low thrust orbital transfers with CubeSats. So the first thing you might ask yourself is, well, what's a CubeSat, right? A cube satellite is a standardized way of building a satellite so that it fits in a standardized deployer, right? So you used to have a specific payload that would deliver your satellite to space and then deploy it. Now they have these deployers that are standardized, so you can fit it on any rocket and then put any CubeSat, right, this standardized format, which is this tiny little 10 by 10 by 10 centimeter satellite, right? So they're light, they're easily deployable, and most importantly, they're cheap, which is why research institutions like OSU and PSU, which both have satellites, and a lot of large engineering schools really, and can now deliver these satellites and do research with them for less cost than ever. And so one of the problems you actually face with this is like, how do you actually keep that satellite in space? If over a period of about 1 to 2 years, you expect that satellite to eventually degrade in orbit and fall out of, basically burn up. Or your satellite stays too long in orbit and it needs to deorbit because there's too much junk in the atmosphere, which is actually a real problem. And it's starting to be administrated that you need to get your satellite out of space after its mission is over, right? And so one solution to do both of those things is to maintain a propulsion system on the satellite. Part of the issues with this is that there is a finite amount of fuel and a finite amount of thrust that you have, especially in such a small volume, right? And so there has to be some planning to ensure you're using your propulsion system in the most efficient way, right? And that's where the mathematics comes in. So I was tasked with this to build or design a propulsion system for a 3U satellite. So that's 3 cubes stacked on top of each other. And we had to establish what the optimal propulsion type was, and then determine how we could actually use that to make orbital maneuvers, right? And determine how we can do that efficiently and how high we can actually get with a given propulsion system, right? And so a part of that is the mathematics of it, is to say like, well, how do we actually use the thruster to make a satellite do what we want it to do, right? And so one parameter we have to start with, just to make a definition, is delta V. So delta V defines how much the satellite's velocity has to change to actually make a maneuver, right? So in the general case, delta V is just the integral of acceleration, right? Or the absolute value of acceleration. But in a single direction, it's just the literal change in velocity, right? There's nothing special about it. But it tells you how big of an impulse you have to put into a satellite to make a given maneuver. And this will become important later. So if we want to actually solve for how to get between 2 orbits, let's take the simplest case we possibly can. That's the general way of doing things. So let's take a transfer between 2 in-plane circular orbits. So let's say we want to go from this red orbit to the purple orbit, right? That's between those two. So there's 2 parameters we have to follow, and that's that the path between those 2 orbits must itself be a valid orbit, and that the orbital path must intersect both circular orbits. You can kind of see that with this picture, right? So the image on the left, the transfer on the left, is valid because it is a valid transfer or a valid orbit, and it intersects both orbits. But the ones on the left and right either don't intersect at some point. You can prove that this is necessary, but I'm not going to do that here, but it's kind of self-explanatory. Obviously, if you don't get to there, you don't have enough energy to get in that orbit, period, right? So and so what we can do, if we know that that's what our orbit has to look like, we can define 2 points, one where it exits the initial orbit, or one where the satellite exits the initial orbit and enters the transfer orbit, and one where the satellite exits the transfer orbit and enters the final orbit that we want to get to. And so the change of velocity needed can be solved for pretty simply. We know what these 2 velocities are, the velocity of the transfer orbit and the velocity of the initial orbit, because those are defined by the satellite's position in the orbit. And that's defined by what's called the Vis-Viva equation. And then the angle between the 2 vectors, the 2 velocity vectors, right, it can be found from the conservation of angular momentum. And so with these factors, we can kind of decide like how to minimize the delta V we need. And we know we can only change the points of entrance and exit to our satellite. And so we can actually solve for this delta V here with the law of cosines. And we end up getting something like this. So it basically tells you that side length of the triangle, right? So we can't change our transfer orbit velocity or our initial orbit velocity, but we can change this last term because it has this cosine of theta. And so by geometrically picking an orbit that fits this the best, we can get the lowest delta V or by maximizing that last term, right? And so this orbit ends up looking like this. So the two velocity vectors, the one pointing in the direction of the transfer orbit velocity vector when you're doing the exit, ends up being ends up maximizing that term because the cosine of the angles goes to 0, right? And so that max cosine turns into 1, and then that term is maximized. And so we call this special case the Hohmann transfer. And it uses the least delta V for an in-plane bi-impulse transfer, right? So delta V has been minimized, but is this actually what we were trying to do in the first place, right? And no, it's not, because a CubeSat can't produce that much thrust. So the example I like to give is that if you held a fifth of a piece of paper in your hand and on the surface of the Earth, the force that it exerts on your hand would be orders of magnitude greater than some thrust that's being produced by some of these propulsion systems. Now, not all of them are meant to get you to the moon, but you kind of get the point of it here. Like, you don't have a lot of impulse to play with, all right? And so when you're talking about that, the Hohmann transfer becomes impossible to make with certain propulsion systems. And so the way to optimize this, when you have this sort of circulating Earth many, many times, is to make a simulation of your satellite and optimize your simulation using numerically, right? So the first thing I guess we would have to do if we were starting with that is to make a model of the satellite that follows the physics of the satellite. So, well, what are the forces acting on the satellite? Well, we're only going to consider two here, right? Gravity and the propulsive force that's acting on the satellite. So gravity is always pointing inwards. It's our centripetal acceleration, and our propulsive force is the actual force of our thruster. There are also perturbations, which is like atmospheric drag, Earth's oblate shape, which there's a ring of mass around the equator of the Earth that pulls the satellite down. There are tidal forces from the moon and different planets that will pull the satellite away from the planet. But these are all pretty low orders of error that they're introducing to our governing equation. And so all we have to do to actually get our governing equation for the satellite is pretty simple. All we have to do is add the accelerations, right? And so what we end up getting, right, we want to minimize some our position and velocity with respect to some final position and velocity that we define. And then we also want to minimize the total thrust that was used. So that integral of u squared term, that's where that's coming from. Because if you're minimizing the amount of the total acceleration, you're minimizing the thrust as well, because that's the thrust is coming from that. And so you can see we have our governing equation and then our boundary conditions, which the initial and final orbits have to be on some set of state vectors that define the initial and final orbits. So now we have to find the boundary conditions, which are the initial and final orbits. So our starting and our final orbits can only be really solved for with numerically. There's really difficult solutions for, or general solutions for orbits, and it's just the easiest if you sort of propagate through our governing equation for the satellite without our propulsive force. And so we end up getting this discrete set of points that this orbit is going to follow, right? And a numerical method has to be used to solve for that. It just makes it the easiest. And so now that we have that, and we can interpolate between those points to actually, or for the solver, right? We have to actually define the problem in Python or some other language, MATLAB or whatever. And so I actually found a library on Python that does this really easily. It's called GEKKO. And so all you have to do is define the system dynamics and our boundary conditions and our conditions that we have to meet for the satellite, right? And it automatically turns it into a problem that the computer can step through and solve, right? And then it outputs a set of variables that's easy for us to understand, or that you can actually turn into a plot and make, your pretty things for your paper, right? So to define the dynamics of the system, right? It's really simple. You can see all we do is we have this equation object and we literally type out the equation. It's pretty simple. I mean, they couldn't make it much more simple. And then the same thing with our objective functions, right? Here was our minimization criteria. We were taking the difference of our state vector, both in position and velocity, and the difference between that and our final position and velocity vectors that we're trying to solve for, right? And so what we end up actually getting when we plug this into the solver is this orbit. And I think this is, I mean, you can sort of say based on the parameters I passed to it, you could get different orbits, but we can say that this is probably valid because it's following an orbit that is the most, or is a valid orbit itself, right? It's not going from this point to then the middle of the or through the middle of the Earth to get to the other side, right? And so we can say that this worked, right? And then we also get a thrust profile, which is the more important part of our thing, right? Because we don't actually care what the trajectory is. We just care about how to make that trajectory with the satellite. So you can see here's our acceleration due to thrust to make this transfer, right? And so we have to ask the question, like, did we actually do what we set out to do? And so, yes, with some transformations, you could take those accelerations that we had solved for and turn them back into a thrust profile that you could eventually feed to your controller on your CubeSat. And all those transformation parts are pretty much the easy part. And then you can determine if a thruster can make that make a maneuver or whatever you want to do with it, if or based on the total impulse that you basically just solve for there, right? And from there, other engineering considerations determine how what the optimal propulsion system is. But this gave us a really good idea about how to use the propulsion system. And once we do have a propulsion system, we can plug this into our model and then solve for what orbits we can make. So the next steps for me are pretty much implementing perturbations. So we want to implement drag. It's a very nonlinear function, and it can change as the satellite, as the CubeSat turns and different faces are facing are facing the direction of velocity, right? And then implementing the different perturbations. Creating a Python dictionary with the thruster specifications. So go online and find a bunch of commercial thrusters, and then find out exact models for them in Python, and then output our thrust profile in a format that's actually readable to the controller. So a discrete set of points that can then be fed to the controller and optimized for right in that way. So, and that is all. Thank you.